two-view geometry. In this particular slide, we will cover the concept of two-view geometry, where if you remember in the stereo vision, we assume we have a 3D object, and then we said, you know what, if we have a viewing point from here, which is an eye here, and then another eye here, then we can find out the difference of specific features here. And these features, based on where you see it in both views, you will be able to find out the 3 dimension. In the two-view geometry, it's a little bit different, because in the in this particular model, we talked about disparity. So disparity was one option. The other option is if I know the source of light and I have a specific distance between the source of light and the camera. In this case, I can only use these two elements to clarify the objects and detect the 3D. However, in the two-view geometry is a little bit different, because I'm looking for two different views, and then I'm looking for similarity. If you remember the panoramic views or any of the other feature matching, it's very similar. However, here I perceive the 3 dimension as part of it. Let's start, and as I always say, if you are concerned with the bandwidth, please stop this video. You can download the podcast and the PowerPoint slides or the PDF slides, and then you can use you can follow audio and download them. If you want to continue seeing the video, more than happy to continue.
This video is subject to copyright own. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the 4 corners on this slide on your screen.
And the readings for this particular session, it will be chapter 7, section 2. If you remember, we just discussed the stereo vision. So we talk about the epipolar lines, and the concept of the epipolar lines is to have one line, and this line will be basically, we can match the features along this line. The concept of the one line comes from the fact that I will have a camera here and then a second camera here. So both cameras will basically have the same view of the 3D object. So here is a 3D object, for example, and then these two cameras will have the same view. However, I will assume if I have an orange camera here, and I will have, let's just have the orange scenario, and I can have an orange camera here. So these two cameras are complete different angles. From these complete different angles, I will have, as what we always say is, we have here a plane, and this plane will represent the image. So the orange cameras will produce the yellow planes. In this case, I'm looking for similarity. So if I have a line here which will go in this direction, this line might be here going in an opposite direction. So these two lines, if I extrapolate them, they will have an angle here, and these angles will play, and then they can also have some sort of difference between these two. So there are few features which we will find out. The epipolar lines are based on the assumption that we are in a parallel view of the actual object, or these particular two cameras, they actually lay over a specific line. However, we assume that this line are always perpendicular of the object or affixed from the object. In the two-dimension view, you will be basically having camera's orientation in this way, so you can have a camera here and a camera here, and then you can produce the output. So if we move next to the next slide, you will have the two geometries. So if I have image 1 and image 2 as what you see here, and O and T are the origins or the imaging, so O will be representing through P a point R, and the epipolar line is the projection of R. However, the point Q will be the point where it represents the intersection. So this epipolar planar comes from the fact that these two images are not on one line. So you have two epipolar lines, and these two epipolar lines, they will represent a planar. So the geometry will have two views, and we have a very special 3x3 matrix called the fundamental matrix F, and the F maps the homogeneous point of image 1 and image 2, and the epipolar line of image 2 of point P will be represented by the FP, and the epipolar constraint will be Q the power transpose FP equal to 0. This will be the limitation. So we will be looking for two special points, and these points will be E1 and E2, which basically these 2 points here represents the line connecting between the two sensors. So if I have a point here E or R, this point will have a representation in the image planar which will be Q, and then a representation here which will be P. And when I will connect these two sensors together, I will have the point E1 and E2. So these special points will represent the projections between one camera to another. So I will be able to build all epipolar lines in the image, and from these epipolar lines through the image I can build a view. So here is the epipolar view. So FP will be associated with the point P, and the F transpose Q will be represented with Q, and F E1 equal to 0, while F E2 transpose E2 equal to 0. And how many parameters we have in the point F? So the question is why the F exists. So I'm here calibrating the fundamental matrix. So I will look at the calibration first. So K1 are the intrinsic parameters of the camera 1, and the K2 are the intrinsic parameters of camera 2. R is the rotation within image 2 with respect to camera 1. So P par will be K inverse K1 P, and this is the ray which is going through the camera 1 and the world coordinate. So P par will be basically the intrinsic of camera 1 inverse of it times P, and this will lead to the point P par over this particular ray, and the Q par will be K1 inverse Q, which basically is a point here which is called R transpose Q. So these 2 points or these 2 directions are the coplanar which form the plane T times P par. So the epipolar plane can be represented as T times P par, and from that perspective there is a perpendicular relationship here, which basically the transpose of this particular vector times T times P equal to 0, and from that problem I will be able to derive that QT or Q bar transpose R times T P bar. So the idea is when you apply the transpose from here inside and distributed, the transpose will become R and the Q bar will be transposed, and you inverse the vectors, which is a very simple vector or matrix multiplication. So if we do one more substitution, so we take the cross product of T, can be represented by a 3 by 3 matrix. So here is T X, which will be a 3 by 3 matrix, which is you have T Z, T Y, T X, T X, T Y, T Z, and then the T time P power, it will be equal to the matrix T X time P power, and from that I will derive the equation where I will be able to find that I will be able to define what we call it essential matrix, and the essential matrix will be Q bar T essential matrix times P bar, which will be equal to 0. So having the calibrated cases as proof is one of the likelihood will come if you have an exam written. If you don't have an exam written, it will be just a multiple choice where it will describe how we can drive the essential matrix. There is a cross product as a linear operator. The useful fact is the cross product with vector T can be represented as a multiplication with a skewed symmetric 3 by 3. So basically I have the T matrix, which is described in this way, and T times P bar will be equal to the matrix T times P bar. In this case, I will have the intrinsic of camera 1, intrinsic of camera 2, and the rotation of the intrinsic. So if I apply inside the original equation, I will find out the fundamental matrix here, where QT times fundamental matrix equal to B. I have to explain that this is if the points are within the same scope. So I would like to talk about in the following slide on rectified case. So in this case here, I have a house, and the original case, if you want to understand how it looks like, so I basically have a plant, then we have a house, and then we have a person besides the house. So this is the full image in front of you, and just to make sure we have a door in the house. So this is the full image. Now you have two different views. So we have one view from here, which basically can see this particular section, and you have another view from here, which can see this particular view. So in this case, I have two views which are not do not have the same object. So in this case, to solve this particular case, I will define R as a identity vector transpose, and the essential matrix will be defined in this way, and then the stereo rectification will look like this. So I have two different cameras. I have the image planes, and then I will go through to locate the object itself. So what's happening here is I can reproject the image plane into a common plane, the plane parallel to the in-between center, and then the pixel motion is horizontal after the transformation, and the two homographic 3 by 3 transform, one for each input image projection. So I have here the reference for you on this particular application. So here I have two original stereo pair. So I have these two stereo pair, and you can see here the polar lines which are not extended of each other, and once I will apply the rectification, I basically will transform the images into a similar plane. So the homography here, or the rectification, basically is I will try to align these lines into being one line. So in this way I can basically remove the effect of the camera. So image taken from the same center of projection using a homography, and it's the same concept we had it before into the panoramic view. And if you have any questions, looking forward to answer them. What we explained here is basically a concept where we assume we have two lines, we have two views, and the two views will come from sensors which they are not in line. And then these images, once they are not in line, I can find the rotation, I can find the new plane for it, and then I will take the plans and I will align them to get the actual object. If you have any questions, please email them to me or ask them below, and I will reply as soon as I can. Now I want to go to the next slide, where I want to estimate the F or the fundamental metrics. I don't know K1, K2, R, and T. However, we can estimate F using two images. Yes, we have enough correspondence, and if we get enough correspondence corner. So if I want to look at the estimation F of 8-point algorithm, and here this algorithm is not meant for you to study it. It's basically, it's an algorithm you can practice in the OpenCV or in the tutorial to understand it. However, some fundamental operations need to be given in this particular course, so I will basically explain it in a nutshell. You should be able to understand the basic idea behind it, and once you practice in the lab, you will be able to have a deep understanding of the actual algorithm. So I will have basically the equation x dash t transpose fundamental times the fundamental matrix time x equal to 0, as what we have it approved before, for any pair matching x and x bar within the two images. So if I have two corners and they match each other, I should be able to apply. So if x will be uv and 1, while x dash will be u dash v dash and 1 transpose, then f will be the f11 till f33. So for each matching equation, I should be able to have this linear operation here, which is the multiplication of uv of x time f time x. So if I do this multiplication, I will be coming to this particular equation where the 8-point algorithm will look like that. So like a homography, instead of solving this equation, I want to seek f, which is minimize the AF, while A transpose time A is basically the least eigenvector. So I will do the F should have rank of 2, and I want to enforce that F is rank of 2, so I will replace F by F dash, which minimize F minus F dash magnitude, and this subject to the rank constraint. From that point, I will achieve that F will be equal to U sigma V transpose, where sigma and sigma bar are defined as sigma, sigma 1, sigma 2, and sigma bar will be sigma 2, sigma 1, sigma 2, and 0. And then I will do the multiplication and I find the solution. This 8 algorithm, I build the constraints for it, and then it's a linear operation, so it can easily implement it. It's suspect to noise, and then I will be able to solve this equation in the order of magnitude difference between the columns. And I would like to show you a couple of things here, where you have to understand that this particular algorithm, it's a complex algorithm, and it takes here is the ground truth. I have here two objects, and here you can see the bipolar lines difference, and with the standard stereo vision calibration, I will use the 8-point algorithm, and using the 8-point algorithms, the geometry is described by 3 by 3 by 3 tensor called trifocal tensor. The geometry of 4 views have been described by 3 by 3 by 3 as a quadrifocal tensor, and after that it starts to get complicated. So for example, here I have the image of Croatia from 2 different points. It took 23 hours for reconstruction, and we have 352 of cores, and unfortunately I could not play it here to show you how it be constructed. So it should be followed up in the lab. If you have any questions on how we do these constructions, I didn't want to go inside the equations because I understand this is a fundamental course, I would leave this to the lab. I want to make sure you have some handle of it. Usually these 8-point algorithms do exist. It's a high complex intensity, and you need lots of computation to perform it. If you have any questions, as always, I recommend email them to me. If you even have a question and you want me to re-explain the 8-point algorithm, I would actually, and I would be happy to have a separate video for this algorithm. Have a good day, and I always remember this is a course for computer vision. It's supposed to have different concepts. There's about 24 different modules in this course, 20 to 24 different modules. There's some hands-on. You have a semester of like 3.5 to 4 months only. You cannot get hold of all these concepts in a great details. However, the breadth of it will allow you to have better understanding. So when you move to the next level and next lectures, you should be able to understand and focus on specific material. Looking forward to hear from you, and have a nice day.